Good morning and welcome to the 2020 Focus on Research Seminar Series. My name is Enrica Ziller, Outreach and Events Manager in the Office of Research at the University of Texas at Dallas. I will be your moderator. As we move through today's session, I invite you to post questions into the Q&A box for our guest speaker to answer. Joining me today is Juan Pablo Vizuet, a PhD candidate in chemistry here at UT Dallas. His research focuses on the synthesis of metal organic frameworks for cancer therapy. Juan, welcome.
Thanks, Enrica, and thanks, Tiffany, for hosting this event. Good morning, everyone. Thank you for coming up, attending this seminar series. And my name is Juan Pablo Vizuet, and I'm a PhD candidate in chemistry in Dr. Balk's lab. And today I'll be talking about the research we've been doing the past few years, particularly metal organic frameworks for cancer therapy. So, well, talking about cancer is one of the leading causes of death worldwide. In 2018, there were more than 18 new million cases reported. And it is expected by that 2030, this number will rise to almost 24 million. And in the US alone, just the 5-year rate survival rate is about 68%. So yeah, these numbers are worrisome. So what are the main therapies that are available to fight cancer? The three main ones are chemotherapy, surgery, and radiation therapy. And we want to focus on radiation therapy for this session. There's two types of radiation therapy: external beam radiotherapy and internal radionuclide therapy. So external beam, you get the radiations aimed from outside your body to the tumor. While the radiation is less, it will take longer time and longer periods of time of treatment to do this. While the internal radionuclide therapy, you are injected with a radiation source. And of course, you'll get high dose of radiation, and this is done in shorter periods of time. And this is what we're going to focus in on today. Particularly, we'll talk about Holmium. So this wouldn't be a chemistry talk if I didn't showcase a periodic table, of course. But most people, you know, they work with transition metals or carbon, hydrogen, you know, organic people. But if you're not familiar where Holmium is, well, you have to look at lanthanides, or the F row, in the F row periodic table row. And in particular, Holmium is right there. But why Holmium? Well, Holmium is 100% naturally abundant as the isotope Holmium-165. And through this process called neutron activation, we generate the Holmium-166 isotope. This isotope has a half-life of 26 hours, and it emits both beta particles and gamma photons once it decays. And here I have a table comparing some radionuclides used for cancer therapy. And as you can see, neutron cross-section right here in the middle will tell you how easy it is to activate this material. And while Holmium doesn't have the highest number, if you go to one of the highest number, the natural abundance for those isotopes is really low, which means that if you want to get really high purity materials containing these isotopes, you will spend a lot of money. While in Holmium is one of the few ones that have the 100% natural abundance. And if you compare to other 100% natural abundance, just like yttrium or praseodymium, their cross-section is lower. So Holmium seems to be one of the better suited elements to work for. And as I mentioned, well, what is this? How does this really work? Well, Holmium-165, as I said, 100% natural abundant, we irradiate it with neutrons, and it will transform into Holmium-166. Now, through this process, it will eventually decay into erbium-166, producing both the gamma photons and the beta particles. Gamma photons, we can use them to visualize these particles inside your body, so we'll know where we are targeting specifically, while the beta particles are the one actually causing damage to your DNA, to the cancer DNA. Suitable Holmium-166 carriers should be nano-sized in preference, should have high Holmium content. We're talking about more than 33 weight %. Thermally stable. We calculate that in the neutron activation chamber, it gets to temperatures about 200 degrees. So if your material decomposes below that, it's not good. Of course, have low toxicity, and in most cases, it is desirable to have a simultaneously delivery of radiosensitizers. What are radiosensitizers? In a few words, it's just molecules that will make the tumor cells more sensitive to radiation. This means that you'll need less radiation to kill the cancer cells. And this is desirable because you don't want to keep hitting your whole body with radiation, just those specific sites you're targeting. Two examples of radiosensitizers are platinum drugs and nitric oxide, for example. Platinum drugs, they open up those DNA chains, which allows other radicals to come in and break the DNA strands. But their main drawback is that there is a systemic toxicity associated with these drugs. Now, on the other hand, nitric oxide acts as a radical, damages the DNA bases, and then that leads to DNA breakage when it tries to replicate. Their main drawback is, while it is present in vivo, the required levels to do so are very low. So the delivery, it is complicated because nitric oxide is a gas. So the delivery to those specific sites is complicated. Nevertheless, some previous work in the Balkus lab have shown very good results. In particular, I want to focus on this structure, holmium iron garnet. This structure is really interesting because we have holmium and iron sites here, and the iron is situated on the octahedral and tetrahedral sites. Each of these irons will have 5 ampere electrons, while holmium sitting on the dodecahedral sites will have 4 ampere electrons. This means that we'll have 12 ampere electrons for holmium in a positive magnetic moment, 10 ampere electrons in a positive magnetic moment for the tetrahedral sites for iron, and then 15 negative magnetic moments from the iron in the octahedral sites. But what that makes overall is a positive magnetic moment, which means our material is magnetic. This will allow us to target specific sites through magnetism. In particular, we can see how this material, the holmium iron garnet, was prepared, and it was loaded with platinum drugs, and it was then activated and tested for lung cancer in rats. And you can see here the difference between no treatment at all versus the radioactive treatment with the magnet, so the black bar and the blue bar, and you can see the actual difference in the tumor volume ratio. Another application, for example, is loading these iron garnets into polymer fibers and spun them into a bandage. This bandage will be then used to cover the skin cancer areas. And again, you can see the difference between the non-radioactive and no treatment versus the bandage in the tumor volume ratio. And there's a patent on this, and right now the clinical trials for this material will begin this summer. Now, going to my research, when I got this Clark student, which I'll talk about later, she's actually trying to get into medical school, and she wanted to work in more bio applications while I was working in metal organic frameworks. So it was just a matter of, well, can we do metal organic frameworks as materials for holmium delivery systems? And before I jump into that, let's define what are metal organic frameworks. Well, these are materials that are composed by metal clusters or metal atoms that are coordinated to organic linkers or ligands. And this will make extended infinite structures that are very crystalline. They are porous. And because you can choose which metals and which linkers you can use, you can tune the pore size and shape. Of course, they have high surface area. There's reports of even more than 10,000 meters squared per gram. Again, their metal organic nature gives them a structural variability, and they are very easy to modify. So some examples is you can modify the metal center, you can modify the linker, You can even change the nature of the linker or change the nature of the metal in the same MOF. So these are very powerful materials. Of course, all the applications that you can use them for vary from sensing, detection, to catalysis and drug delivery. We know we're going to use Holmium, but what about the linker? Well, we just look at literature and it's really easy to see which one is the most commonly used linker. And it's this one down here called terephthalic acid. And here are some few examples like MOF5, which is a zinc-based MOF, the first MOF ever reported by Omar Jagid. A zirconium MOF, which is very stable in water, or a chromium MOF, which is one of the first reported to have breathing behavior. But why is this the most common linker? Well, it is a commodity chemical. It means it is used as a precursor for polymers. So it is easily available and it's really cheap. Because it's just a linear linker, it imparts rigidity to the material. It forms strong coordination bonds, specifically with lanthanides and holmium. It will coordinate really fast and really easy. It has versatile coordination modes, and there are several derivatives available. What do I mean by coordination modes? Well, it means that it can bind to different the metal centers in different ways. This will open up the architecture that we can build through this linker. Now, what do I mean by derivatives? Well, you can add almost any functional group, organic functional group that you can think of. So you can have amines, hydroxy groups, nitro groups, etc. And of course, as I mentioned before, you can modify the nature of these linkers. So having an amine group in there is very powerful to doing post-synthetic chemistry. Now, how are these made? Well, the most commonly method for growing these MOFs is solvothermally, which just means you have your holmium salt precursor and your linker precursor, and you dissolve them in a common solvent, and once you heat them up, these metal ligand coordination bonds will start forming and breaking until it actually stabilizes to your desired product, and it will come out of solution, and that's how you obtain your MOF. Of course, you can modify the pH, the initial pH of your solution. You can modify the concentration of your precursors. You can change time, you can change temperature. All these variables, while they seem minor, they really impact the final structure. How do you characterize them? I would call these are the three essential methods of characterizing. There's really more, but these three ones are the most important ones, where you have X-ray diffraction, either single crystal or powder, thermogrammetric analysis, and gas absorption measurement. And I have down here this scheme of synthesis, where we can go through each of the steps. So once you make your material, you want to know the structure that you have. And that's when you use single crystal X-ray diffraction. Now, if you already know the structure and you just want to compare it, then you use powder X-ray diffraction. That will instantaneously tell you if you have the corresponding structure. Now, in most of these materials, since they are porous, they will most definitely have solvent residue inside. And that's when you use thermogrammetric analysis to know exactly at which temperature you get rid of the internal solvent. And it also tells you the thermal stability of your structure. And finally, once you have those empty, nice pores, you measure the gas absorption measurement. That will tell you how easy and what sizes and shape are those pores. But I do want to highlight how important is X-ray diffraction for us. Since we were working with new structures, single crystal X-ray diffraction is crucial. And if people have done some crystal growth for proteins or for other molecules, they know this is challenging. But if you're not, let me just show you a couple of examples where you look at these crystals and they look really nice. But take, for example, the one on the left. They look really nice. You can see all the facets in the crystals, but once you see the size of those crystals, they are not suitable enough for single crystal X-ray diffraction. So you need to go back and change your synthesis conditions until you grow bigger, good quality crystals. Now you go to the right and you're like, well, these are bigger, but you can see that these have multifacets on one crystal. This is called twinning. And this really makes it very difficult for the crystallographer to really try to get your final structure. And as I said, you have to go back, change those conditions over and over and over until you get a nice, beautiful crystal like this. So let's jump into it. And I have to give a big shout out to these two undergraduates. They were Clark students, and they did most of helping me getting all these structures done. Abby and Julie, they know what it means to keep going back because you didn't get a good crystal, so go back and change the pH or change the concentration. So a big shout out to them. And we'll be looking today at just 3 different synthesis conditions. We'll see the effect of the solvent, the effect of the pH, and the effect of temperature in making these Holmium MOFs. So in particular, solvent, I want to look at 4 different solvent systems. And the first one was the most obvious one, which was water. And here, I'll just do this highlight for this particular structure, and for the other ones, you'll see the same moieties, but you'll get it. So coordination number, Holmium and several lanthanides compared to coordination transition metal elements, they have higher coordination numbers. So if you talk about zinc, you know 4, nickel 2, they are very common. But once you get into lanthanides, you're getting something between 8 and 12. So this coordination number will really open up the architecture that you end up with. In particular, here we can see that we have one unique Holmium crystallographic site. Each one of them will coordinate to water and the linker. But what is interesting, and this is what we call repeating units, so you'll take this unit to the left and just repeat it over and over and over in 3 dimensions, and that's how you visualize the final MOF structure. But it's made of dimers. So there's 2 Holmiums that are the core of this repeating unit. And as you can see here, these dimers repeat over and over to make a chain. And then these chains are linked by the ligand, terephthalic acid, in both this direction and this direction. So you end up with a 3D framework. Now, in this case, this is a not very porous framework, but it is still a MOF. And this is what I was talking. I'm not going to show all the characterization for all of them, just for this one, so you understand what I was talking about. So once we got the single crystal, we can predict what the powder X-ray diffraction pattern will look like, and then you compare it, and you know if you're actually synthesizing the structure that you want. You have to look at these peaks, see if they match, and then you know you are producing your expected structure. Then you run TGA, thermogravimetric analysis, and here you can see these 2 solvent drops. So we know that the material is stable to up to 500 degrees. And as I mentioned before, 200 degrees is what we think the reactor gets at. So this is a very promising material. And you finally run PXRD again, just to show that after you do the evacuation, this process of removing the solvents called evacuation, you run PXRD again just to show that you still have that structure intact. As I showed you before, the structure it doesn't look very porous. So when I ran gas absorption measurements on this sample, it wasn't good. But now now let's go into more synthesis conditions. So here we start changing some of these conditions. We have, for example, a different solvent, DMF. And what this did was it did change the coordination number around Holmium centers, and it changes just how the linker behaves, how the repeating unit changes. Now we see DMF in the structure, but then again, there's a dimer at the center of this repeating unit. And you can see the dimer here more clearly, and it's the same. The dimers are connected by the terephthalic acid ligand in 1, 2, and 3 different directions. So you end up with this nice porous structure. The main problem or the main drawback with these ones is the pores are so big that you end up actually growing a second MOF inside those pores. This is called intercalation of MOFs, and is a very common problem, especially when you're trying to build these huge cages of huge pores, because the space is so big that it will allow another linker to go in there and start creating this MOF around the other MOF. Now, what if we get rid of water? We change the coordination number again. So we have 8, 9, and now 7. Now we only see the MF coordinated to the centers. But then again, the repeating unit is dimeric. We have 2 Holmium sites. And very similar to the previous ones, but now here you can actually start seeing those diamond-shaped pores once we remove the DMF from those centers. And just to follow up on this, we changed we changed it slightly. The solvent that we use, so DMF and DEF is literally just 1 carbon more in the solvent, and everything stays the same. Coordination number stays the same. Dimers, everything stays the same. And if you look at the structure, it almost looks exactly the same. The only thing is the pores do seem to be a little bit larger once the solvent is removed. So that tells something about, okay, the nature of the solvent really affects the final structure, but when you're dealing with similar solvents, they behave almost the same. Now, what happens if we concentrate on different pHs? And now we switch, instead of terephthalic acid, we'll use one of the derivatives, by pyridine-based linker. And we were very interested in this because it has those nitrogens in the rings, which will maybe allow us to bind something in there. So if we go back to the intro, we want radiosensitizers. So maybe this group will allow us for complexation with platinum or nitric oxide. And this is with no acid, so the pH is a little bit acidic due to the nature of holmium. We use holmium chloride and holmium nitrate as our precursors. So these will make the solution slightly acidic. And as you can see here, only water coordinates. But you can see again, we're talking about dimers. So dimers is a prevalent structure motif that we see here. Now, if we change, and this is normal when you are trying to grow single crystals, one way to slow the growth of these crystals is by adding acid. And if you slow down this growth crystal, then you end up with nicer, bigger crystals. But what we ended up here was a change in the coordination number. And now we actually see our solvent DMF. In the previous one, we also had DMF, but it didn't react with the Holmium center. But here it definitely did, and it changed the whole structure. Now you can see how it got a little bit messy in there. Bigger chains, but again, non-porous due to the linker in there. But that tells you not only the solvent is important, but your pH control will also definitely affect your final structure. Finally, I'll just want to go into the effect of temperature. So here we were playing with a naphthalene dicarboxylate linker, and we actually observed 3 different structures just by changing 3 different temperature conditions. And again, the main thing we see is there's a dimeric cluster in the repeating unit, and coordination number will actually change. So we have this final structure, which again doesn't look that porous, and we actually see some bending of this naphthalene, which was something that surprised us at the beginning. So we went there and we increased the temperature to 120, and we changed it with this. Just with this increase in temperature, we changed the coordination number, which again just led us to a change in the structure. You can see how it is vastly different from the previous one, and it is just a 40-degree temperature change, which when you're talking about a DMF, it's really not that much, since the boiling point of DMF is 150, 160. So yeah, it shouldn't be that much of a difference, but in this part, in lanthanides in particular, lanthanide MOFs, these are critical. And finally, well, we went beyond the boiling point. And this is interesting because we actually don't see any solvent coordinated to the metals. We still have a dimeric Holmium center cluster in the repeating unit, but no solvent in it. And you can see we still see some bending of that linker blockage, but no solvent in there, which is very interesting, very promising. So yeah, these are some of the structures that we were looking at. I mean, as I mentioned before, you can add nitro groups or hydroxy groups or amino groups to these to open up your structures. But after doing, I mean, I just show some of the structures that we have done. We have dozens that we have prepared and characterized. But there was one thing in common, and I think I mentioned all of them, but in case you miss it, all of them have these dimers. So we thought the key for stabilizing and growing these materials may lie in the nature of that dimer cluster. And first I told my advisor, oh, it is because, you know, we're using terephthalic acid. It's just a bidentate ligand. What if we have 3 of them? And even in some of those, you can see that there's still dimers. It's just chains of dimers that go along. So what is the reason behind this? And well, we end up finding out that people are actually interested in lanthanum clusters for different applications. And turns out that dimeric cluster is really, really common if you're working at the conditions that most people synthesizing MOFs are at. So we're talking about low pHs. Anything below 5 will tend to go through a dimeric cluster. If you have amide type solvents like DMF or DEF, carboxylate-based ligands also apparently help getting that cluster precursor formed, which terephthalic acid and trimesic acid, which is the trisubstituted linker that I showed before, and the counter ion effect, which comes from the chlorides and the nitrates from holmium chloride and holmium nitrate that we use as precursors, that also helps build this dimer cluster. So what happens is these conditions, when you first mix all of these, which you don't think is happening that much, what you're actually forcing is these clusters start forming right away because these conditions really favor these clusters. So once you make these clusters, then the MOF is built around them. The terephthalic acid comes in and substitutes those hydroxy groups, and that's why you see them in all of them. And this is not uncommon. If you go into looking into other MOFs, for example, ruthenium MOFs are built around a ruthenium cluster, which people first modify that cluster to then build the MOF around it. Or the zirconium MOF that I showed at the beginning, you can actually synthesize the cluster first and then start modifying to build the MOF. So of course, the question is, well, can we actually avoid the dimer cluster and do something bigger? And this is what we're actually going to try in the next few weeks is finding some conditions, which I think we found some promising literature that points out at what conditions we can work to get tetra or hexa nuclear clusters as the base for our MOFs. And we hope these larger clusters actually make our materials more stable and suitable for the applications that we want. Now, to the second part of my talk, I want to again highlight the work of these amazing undergrads, James and Julie again. Julie was working on some of the synthesis, but we were having so many problems that I was like, well, let's switch it up and let's try getting you into some of these delivery systems. And of course, Thomas, which he started this a couple of years ago, but he graduated. Yeah, big shout out to them. And let's jump into this application. So the first application is delivery through magnetic particles. So this is very similar to the garnet, but the problem, a little bit of the problem with the garnet is it is not as strongly magnetic as magnetite, for example. So when you want to target something that is in deeper tissue, it's harder to get there. My lab mate, Jason, he was working on trying to get magnetite and some silica cover to get the holmium transported. But we actually thought, well, what if we coat this magnetite with the MOF system? Can we actually end up with a delivery system that is magnetic and has the holmium and has the porosity? And we actually got a grant from Context. Context is a participation between University of Texas branches and Mexican universities. So we got the grant to start working on this. And the synthesis is really as simple as this. Once you get the magnetite, it's just basically the same synthesis conditions that we've been working through. Now, the only difference is we are trying to find how the magnetite itself affects the synthesis conditions. And we have noticed that even if we cut the times by 10% of the original, we still see a huge increase in crystal growth. Now, magnetite itself, it might not be as suitable to grow the MOF around, so we were trying to think about anchoring molecules that will help us build this MOF around it. That's why we chose cysteine and TGA, thioglycolic acid, because this moiety, the sulfur moiety, will bind to the magnetite and we'll leave these free groups on the surface. Now, as I highlighted here, these groups are exactly the same as the linker. So Holmium will try to bind to those groups, and then we can start building them off around those groups. And some quick results that we got before, this is SEM pictures and DEM pictures of pure magnetite with the MOF around it, cysteine magnetite with the MOF around it, and the TGA magnetite with the MOF around it. And as you can see, the best result by far is the TGA. Even though we still see big crystals, it seems that they are composed of little particles, the same with the magnetite. All of these three are actually magnetic, which is very promising. This is exactly what we wanted. And through XRD, we can actually confirm both the presence of magnetite and the presence of the MOF. Now, in the case of cysteine, it's a work in progress. We're still not sure what happened, but it is magnetic, so it might just have changed the nature of the MOF synthesis conditions and the product. But overall, even though this looks very noisy, this is mostly what you want because you can still see the peaks of the MOF in there. They're just very small compared to the magnetite, which means your coating around the magnetite is really thin. And this is something that you want because you need smaller particles to be able to inject them. And now to James' work, we have holmium thin films, and we're thinking about brain tumors. Brain tumors, we have the blood barrier, brain barrier that doesn't allow for particles to cross through that easily. And sometimes, and many times, it is very hard to operate on brain tumors. So we had this idea of having this film where maybe you can do a small opening, insert this material for 2 or 3 hours, let the radiation work, and take it out. And use this process to treat those hard to access tumors. And how these thin films are usually grown is through self-assembled monolayers. So you have your substrate, and you need some type of, similar to what we did with the magnetite, some type of anchors. Then with that anchor, you get your holmium or your lanthanide salt and your linker, and that's how you grow the MOF film on top of this. And James has been working at this for about a year. And we developed 3 different techniques, or we had taken advantage of 3 different techniques. Our first approach was, of course, well, what if you get just your glass, put it in your monolayer solution, see if it grows, and then we'll go for them. But it wasn't working as well as we expected, so we started looking at other type of processes, and we end up with spin coating, where you spin at really high speeds, rotations, and what this allows is for the monolayer to assemble really evenly on the surface, and the spinning will cause the solvent to evaporate faster than just sitting on top of it. And the last, and what I didn't mention here is the monolayer that we are going to use in these 2 cases is this molecule here, this silane in the middle. So very much as we did in the magnetite device, we use the silane group to attach to the glass, while we have this free group that reminds you of the linker attachment, functional group. The last one we actually tried and looked very promising too at some point was spray pyrolysis. So spray pyrolysis, what you do is you have very small droplets through an atomizer, and these droplets get in contact with high temperature surfaces. This allows for rapid evaporation of your solution, like water or your solvent, leaving behind just a thin film of whatever material you want. In particular, we were looking at lanthanum chloride solution, water solution, and the moment it hits this high surface, high heat surface, I'm talking about 400 degrees, 500 degrees Celsius. So really high temperature surfaces. The moment it comes into contact, these are very small droplets, so the water really evaporates very fast and evolves into chlorine gas and hydrogen gas, but it leaves behind a lanthanum, or in our case, a holmium oxide film. This is a very thin film that then we can use to build the MOF around it. And synthesis conditions are really not that far from what we've seen before. The 3rd time's a charm. Just instead of magnetite, we will go in and put the prepared glass slide, either by any of the methods that I mentioned before. Use your holmium salt and your linker. Here, we actually haven't seen any change in the synthesis results. As I mentioned, magnetite did some modifications on our reaction times, but as long as we have seen on the glass, I think we actually have to adjust for the time the glass needs to be in there to just have a thin film. Because if you leave the glass longer, of course you end up with big crystals on top of the glass, and that's not what you want. You just want a small thin film. That way it is easier, it won't be as easy to scratch. You don't want anything to be left behind when you are inserting something into the body, right? So thin films are ideal for this, are easy to transport, and it won't be as delicate as having big crystals on top of the surface. So yeah, the only adjustments we have done so far are just time. And sadly enough, I don't have ACM results. We were finishing all this project when the quarantine started, but we did have the XRD results, PXRD. So on the bottom, you can see the single crystal simulated pattern from the MOF, original MOF, and on the top the thin film. So this is just from the process of immersion. And I was mentioning, this didn't seem as well as we wanted. You can determine it is the same MOF, even though there are still some extra peaks in there. You can determine it is the same material. But one characteristic from thin films that you can determine through XRD is the disappearance of some peaks. And these peaks, they will disappear because there's an alignment when you grow these crystals, this crystal surface. And thin films are characterized because they are so thin, they are really so small that they only grow in one direction. At the moment you start seeing more directions showing up, that means you are having polycrystalline material on the surface, which means more than just one crystal phase is growing, meaning you have more than one thin layer of crystals. Now, spin coating, that actually started giving us better results. As you can see, the intensities from these two peaks are, this one is more decreased than what we hope to see. So there is definitely some growth that we are hoping we're getting. But what gave us the best results so far is the spray pyrolysis result. As you can see, or what you cannot see, is the rest of the peaks. You can barely see some signals in there, and they are repeating signals. So we can go back to the single crystal structure and say, oh, it's growing into the 100 plane, because this peak here shows up, and this little one in here, and this little one in here. But the rest of them, they don't show up. That means that the film is really thin, and it's just growing into that 100 plane. So we have that preferred growth orientation that is, again, as I said, PXRD will show you right away. So as I mentioned, we do not have the ACM results to show along with this, which is really sad because these were very promising results. But once we get up and running, we'll definitely get those. So overall, I think we're almost there in the part of the delivery applications. The magnetite system needs a little bit more workout and a little bit more characterization. And I have to say the same about the thin film. They look very promising. It's just finding some of those nice conditions and, of course, be able to reproduce it, which is very important in science. But other than that, once we get those perfect systems, we are ready to test them, see if we can activate it, see if we can load some radio sensitizers on them, and we're good to go. So, just a final overview of what I've been talking about all this time is, well, I just show you several of those Holmium MOFs that we have made in the lab. I mean, again, it is very hard to get a single crystal, and we're talking about like more than 24 structures that we have done in the lab so far. A lot of them with the help of undergrads. So again, a big shout out to them. And those crystals were good enough to solve by X-ray diffraction. We also characterize them by many other ways. But in particular, we try to drive the discussion into how are these MOFs grown, how are these made, and once we understand this underlying mechanism, in particular that dimer that show up in all the MOFs that I show, now that we understand it, can we take advantage of it to grow better systems? And of course, I just finished with the delivery applications, which are currently underway, and as I mentioned several times, they're very, very promising results. It's just fine-tuning. So with all this, I just want to show some of the publications that we've made, some finished manuscripts that are just being polished before submission, and some of them are in preparation, but yeah, very rich field we have here in the Holmium MOF. And finally, I want to acknowledge, well, again, UT Dallas for hosting this whole seminar, and of course, Enrique and Tiffany for hosting this session and helping me along. our founding institutes, Welch Foundation, Context, and me personally, I got a scholarship through Conasi to come here and do the PhD. My advisor, Dr. Balkus, my community members, Dr. Ferris and Dr. Moselman, our in-house crystallographer, big shout out to him because none of this could have happened if we didn't have those structures, as I mentioned. So Dr. McCandless, of course, all my friends in the Balkus lab. Here, just a few of them, highlighting them with Holmium at the back. And of course, again, I showed them before, but big shout out to these three guys. And thank you all. There's my contact info if you have any questions, but of course, I'm open to questions right now.
Great. Thank you so much, Juan. We do have several questions in the queue. The first one, how can the solvent change the coordination number? When you used water with DMF, it is CN equals 9, but water CN equals 8 and DMF yes. CN equals 7.
Yeah, so it goes back into, I guess it's finished with this, but it goes back to this. Those little changes, it doesn't seem that much, but the presence of that amide group just affects how this precursor cluster behaves. So for now, at least for us, it's very hard to predict exactly what will be the final structure, but for sure, this is modifying this cluster, the speed of this cluster, how easy it is for the linker to access. And this is what we found and we're trying to go into is some people have used fluorinated compounds to actually change how you access this cluster. The slower you can work through this cluster, the bigger you can actually get. So I hope that I answered that question.
Great, okay. And then what is the reason when you used acid HCI at the moment DMF can bind to the structure in slide 41?
Slide 41, okay. Well, yeah, as I mentioned, I think I didn't cover why I use acid, but one of the most common techniques to grow crystals is this controlling the speed of the reaction. And you want to slow down the reaction slow enough, not stop the reaction, but slow it to the point where those crystals have time to grow into the suitable size. You know, the faster you go, you tend to get those small, they could be very nice, but they are small. And we're trying to get those large crystals. So that's why we start adding the acid. Because, yeah, we're having some problems getting this one. We actually got this structure first. And then after some modification, we got this structure that we have observed before in powder X-ray diffraction. We just, didn't have the single crystal. So that's why we added HCl to this one in particular.
Great, and let's see, maybe this person missed it. I wanted to know the purpose of magnetite. Was that just for making the particle smaller, or was there something else?
Oh, no. Yeah. So just going back to it, let me actually go a little bit to the intro. We were trying to kind of replicate what we have done in the lab before, where you have these magnetic particles. In this case, they had holmium iron garnet. So you can, by putting an external magnet, you can try to direct them to the tumor site. Now, I did mention one of the few drawbacks of this material is the magnet strength is not as high as you desire. So you need to work with a lot of big magnets, and the deeper you go into the tissue, the harder it is to get. So magnetite is a more effective magnet. That's why we're trying to use the magnetite and then build a MOF around it to have the holmium. That's the reason. And of course, yeah, the magnetite has to be very small, and the coating around that magnetite also has to be very small, so we can use it.
Okay. And you are, just so you know, Juan, you're not in presentation mode, so the slide is smallish.
Yeah, sorry, I go back, but I forgot to.
Yeah. The next question, what are other examples of characteristics of MOF other than X-ray diffraction and the other two that you mentioned?
Oh, other characteristics. Well, I mean, you can go through the basics and go through infrared spectroscopy. You can do NMR because you have those organic linkers. So it's just a matter of, you can do a solid state NMR if you have access to it, or you can dissolve the crystals and look at just normal NMR and look at those. What other characterizations? Well, there's instances where if you cannot grow big crystals, you can use synchrotron instead of X-ray diffraction, which is just very X-rays. Let me see. Well, you can use TEM. There's this recent report where they look at the pore size of C8, a very common MOF. But they had access to this cryo TEM where the electron beam wouldn't destroy the MOF. So you could actually see the pores in the structure, which is very interesting. But as I said, those three are really your essential ones. Like if you go to any MOF paper and they are talking about new structure, those are definitely the ones that they need to be there.
Okay, thank you. And the next question, why is it called magnetic moment? I haven't heard that way of wording it before and was curious why it's phrased like that.
Well, this is more of a physics term, so I wouldn't trust me 100%, but yeah, basically it's like it's a force, right? So it has a moment, and depending on how they are oriented. So let me, I think it's here, right? So in this case, it's not very clear from the picture, but some of these ampere electrons will have a direction. And we said this is the up direction and the down direction, and that's, it's a force, so it has a moment to it. But yeah, I mean, I'm not great at physics. I know physics basically, but yeah, I guess that's the gist of it. That's yeah.
Excellent. Okay, thank you for clarifying that.
No problem.
And why do multiple facets make these crystals unusable in your research?
Oh, well, so yeah, I guess I didn't include that. So if you're not familiar with single X-ray diffraction, then I can see why. But what the crystallographer does is he takes this nice crystal and he mounts it in the machine, and then he shoots X-rays at the crystal. Now what he gets is actually a map that is made by different points. It has to be points. So then he captures these points in a 3D space and through different programs and what he knows how to do it, he can build back this diffraction to be like, oh well, these points are a zinc, or this is a carbon, or this is holmium. But when you have these crystals that have so many tiny phases, so even if you grab this, this is a 10 micron scale, so you're just able to pick this up. It's hard to break that little phase in it. So when you mount it in there and you start moving the crystal around, the point that you see here will be a little bit distorted if you move it around, because this phase has a different orientation. So now it will be a misinterpretation of your data. It is really hard. That being said, people have substructures with these twinning problems. It's just when you see so many of them, that is very hard. When it's just a couple, 3 or 4, people can work around those because of symmetry.
Okay. And I think so far we have just one more question.
Okay. Yeah.
And we've got about 5 minutes left. So last call for questions. If anyone out in the audience still has any, please do submit them. Juan, what led you to your interest in conducting this kind of research?
Oh, well, so, I mean, when I joined Dr. Balk's lab, well, first, quickly, I have to give a big shout out to my advisors. When I first met him, he was very straightforward, and I like that about him. So yeah, I mean, I joined his lab with no problems. And I joined the membranes team, which I didn't talk about membranes here at all, but that's also something that I do, is we do gas separation through polymer membranes. And one of the main things that they have done is the use of MOFs, incorporating these MOFs into these polymer membranes to help the gas separation because they have these nice pores. So I was just working on trying to make some of these MOFs some of other MOFs usable for gas separation membranes. But yeah, along came my first Clark undergrad, and as I mentioned before, is she was very determined to be a doctor, and she wanted more a bio approach. So I had time. I was just on my starting my second year, so I was like, well, sure, let's. I talked with Jason, which I mentioned before. He also works on the Holmium side of parts, so it was just a matter of getting all these pieces together, and we just started making crystals and making more crystals and structures and all this. So, I mean, it just happens.
Excellent. There are no more questions. Juan, do you have any closing remarks to make?
No, again, I'll just like to thank both of you for hosting this seminar, and everyone that came in, asked questions. And again, there's my contact information. There was my contact information. So just, if you have any more questions, you can ask me.
Great. Well, thank you again for sharing your time, talent, and resources today, Juan. I invite everyone to join us 2 weeks from today as we welcome Dr. Nikki Delk, Assistant Professor in Biological Sciences, to the third 2020 Focus on Research seminar on June 12th. Please see the announcement in the Q&A section for the link to view the complete seminar schedule and to register. Thanks again for joining us today, and have a great afternoon, everyone.